Okay, in this lecture what we're going to do is we're going to talk about some of the variables that are going to come up in our beam equations, and in my opinion it's very important to understand to different levels of degrees what these actually are. So we'll just talk, there's 6 here. So the first one to understand is the variable that is the distance along the beam. So we have some kind of a beam, no matter what the support is, there's a certain point that we will, and usually want to choose it to be the left side of the beam. Now we choose that. You could actually be the right hand side of the beam, but you choose over here to be x equal to 0. You can do everything starting from the other side. Now usually if it's fixed ends or simply supported, it starts where the support is, and maybe I'll show that for simply supported. So simply supported, I'll just support this side. Might look something like this. And this is where x equal to 0 is. Now, so what that means is, like, now we won't worry like about this little bit too much, but essentially, like, if we're talking about a 6-meter beam, in our questions might actually be longer because of this slack here. So this is where x is equal to the length of the beam, or excuse me, this is x equal to 0. And then the other support is the span of the beam. Okay, so this would be x equal to the span, for example, it might be 6 meters or something. And usually we'll use the symbol L to represent the span. So if you're talking about x, it's a certain distance along this. So from x equal to 0 to x equal to L. So for example, maybe at 1 meter, if I talk about x equal to 1, it means 1 meter along. Now, one thing that you might see, or I might have seen in your other things, is maybe I'll have a point load here and another one here, and you're talking about the distance between them. You won't do that here. So what I'm talking about is, say if this was x equal to, well, maybe try and make it some kind of sense. So if this is a meter, you won't do meter, meter, you'll just call this 1 meter and this 2 meters. So basically it's an axis that goes like this. So x is the distance along the beam from the left support. Okay, so that's distance along the beam. The next is load per unit length at a point. So this one is a little bit trickier, and we'll probably have to give a kind of a weird definition, but we'll do it. So now I won't draw supports this time because that's really not important here. Oh, it is important because I need to talk about x equal to 0. And when it says the load at a point, all the points along the beam are given in terms of x, the distance from x equal to 0. So just to make this thing a bit clearer. So if you're talking about this distance here, would be 2 meters, not 3. Okay. So now actually what I'll do is I'll just assume that the support is on the end. Okay. So the x is equal to 0 here. And now what's the load per unit length? There is a subtlety about the load per unit length that we'll talk about. So now this might look like a weird definition. Okay, this will be the x-axis, and this will be the w-axis. So the load at a point will be w at x. So basically, so you're going to have a load, and so if I graph the load per unit length, now you're kind of familiar with things like UDL, something like this, but this is actually can be defined more generally. It doesn't have to be UDL. So say, I need to stop this. Okay, so here, say at this point. So this is a distance x along the beam. So the load per unit length is, if you just stop here, look at the load at that point, and suppose that the magnitude of the load didn't change. So here, like, here's constant for this period, and then it kind of changes. So the load per unit length is, imagine 1 meter of the same magnitude of load. So this would become x plus 1. Then this is the load per unit length at x. Okay, I think the idea you want to think about it is it's kilonewtons per meter. So here, for example, so this is over 1 meter, and so this is supposed to be this is the load in kilonewtons. Okay, and so what it's saying is that if the magnitude of the load stayed the same for 1 meter, that you would have W of x kilonewtons here. And so you've got this, say for example, for argument's sake, let's say 18. So if here the load per unit length is 18 kilonewtons per meter, and if it stayed at that magnitude, so if you had 18 kilonewtons per meter and you have a meter of that load, then this would weigh 18 kilonewtons. So the units, we can write something for units. So the units of load per unit length are kilonewtons per meter. And then you kind of think about, so UDLs are easy. Linear loads are a bit more complicated. We'll see what a linear load is. The point load is kind of weird, because with a point load, we're actually imagining that the width of it. So say for argument's sake, this was, say this bit of UDL, say for argument's sake, came to 1.2 meters. And this is from x equal to 0. And say again, for argument's sake, that this was 72 kilonewtons. Then the load per unit length, and this would be the same, it's from 0 to 1.2, so I'll just put in, for example, at 0, would be the total load over the total length, and I think that comes out to 60, if I'm not mistaken. Yeah, 60 kilonewtons per meter. Okay, I hope that you can see that. So what you have is a load distributed over a length. Now the point load is going to be kind of complicated, because now what you can think of a point load is that it's a UDL of a very, very narrow piece of the beam, like a centimeter if you want. And so then you're going to get a very, very large load per unit length. So for example, imagine a point load, and I think we're going to do this a bit more later, so we'll see it again. Imagine a point load of 18 kilonewtons over a single centimeter. So it'll be 18 kilonewtons divided by a centimeter in meters is 0.01. So you're getting 1800. So what we actually do with point loads is we don't pretend that they're little UDLs over like a centimeter. We actually push it and say, oh, it's a UDL over a millimeter, a micrometer, a nanometer, and you make it smaller and smaller and smaller. And as you make the distance smaller, say to millimeters, micrometers, nanometers, you see that the load per unit length due to a point load is getting bigger and bigger and bigger, and essentially it's infinite. And we'll get back to that a little later. But that's what the load per unit length is. It's you kind of need to go over this meter if you got the load varying. Obviously, if it's a UDL, it's simple. You just do the total load divided by the length, no problem. But if it's changing, you got to say, okay, stop at this magnitude, go for a meter, and that's what you want. There's probably other ways of doing it, but that's possibly the easiest. You should, of course, also be familiar with this concept from your engineering, and everything that you know from your engineering, please bring it into this module. Okay. And the next one can be kind of defined a little bit differently, but I'm just going to take this definition. The shear is something that you probably know actually better than me. So what I'm going to do is let's draw a. I think it's. I'm trying to think now. Yeah, so this might be a funny definition, but we'll just go with it. I think I'm going to make this the load versus this. So suppose the load, for argument's sake, now we'll take a span of the beam to be L. So the beam is going from here to here. So let's just do a mixture of loads. Now you would draw a UDL like this. And I'll do that as well, but mathematically I'm thinking it's more like that. And then we'll do a point load. I suppose there's another kind of a load knocking around here, isn't there? The reaction load, the reaction at A, etc. And maybe there's some kind of bespoke weird load here. Okay, so the definition for the shear, let's do this crack again. So the definition for the shear at a point is the sum of the loads here. So V of x is, let's call this x0, is equal to the sum of the loads up to that point. A good question is what if it's at I think it should be less than or equal to, in case there's a point load at the point you're looking at. So this would be, I'm just going to write the loads. Now there is a relationship between these two, which we're going to learn about. The derivative of the shear is minus the load per unit length. I think that would be there's a bit of a choice of sign, but how does the shear change? That's the derivative of the shear, is related to how much load you have. If you were at a period here of no load, the shear is not going to change between here and here, because the sum of the loads from here to here is the same as the sum of the loads from here to here. And maybe I should also include the reaction. It's a little bit messy. There could be like a minus reaction or a plus reaction. It'll all come out in the wash for us mathematically, but for us the shear is basically the sum of the loads. Okay. The bending moment is something that I don't really understand very well, no matter how long I teach this, but it's something that you're supposed to know at. It's a similar story, but it's the sum of the moments from x up to x at the point. Okay, now the ones that I think are a little bit newer are the slope and the deflection. And you have to understand these. If you confuse these two, you're going to get into all kinds of trouble. So I think what we're going to do is we're going to show a exaggerated deformed beam. I think that's what we're going to do here. Yeah. Okay. So let us draw some axes again. So this is going to be the x-axis. Now this time, so that's the distance along the beam. And we're going to draw the y-axis. Now this is not the load. This is the actual deflection of the beam. And we'll show exactly what deflection means. Here is the span, and we're going to consider, and of course this is x equal to 0, which wrote in there, we really shouldn't, but we will. What we're going to show is there's a load here, I'm not going to draw it, and I'm going to exaggerate the deflection. So the loads will cause moments, which will cause the beam to bend, and imagine that the load is simply supported or fixed ends. Let's exaggerate what the beam looks like. Now actually we don't have to exaggerate, we can just say that they're different units. So x could be in units of meters, and maybe y is in units of millimeters, and we don't show the scale, so it doesn't really matter, but this is how you get, so you can, if you want to get a graph like this, such an exaggerated graph. So let's say y is measured in millimeters, and in fact it is in the equations that we use, and x is measured in meters. Okay, so what is the deflection? Now there's a kind of a weird thing going on, because the beam actually gets longer, but we're going to actually in a minute write down the assumptions of our model, and I think one of them is that the beam doesn't actually get longer, or whatever, it's all, we don't worry about it basically. So take a point x0, so that's just the distance along the beam, and look how far away from the neutral the beam is. Now we assume that the beams do not deflect under their own load. Of course, a real beam will actually deflect on its own, but we're going to assume that it doesn't deflect on its own and it goes straight across. Now you can even have pre-tensed beams that will deflect, but they actually start they look a bit like a U shape, and then when you actually put them down, they deflect under their own load and they're flat. But anyway, the distance, the vertical distance between the neutral and where the beam is after loads have gone on it is the deflection. And you have to understand that for simply supporting fixed ends, and we might do some of these up here, the deflection at the span, if it's fixed over here or supported at all, well, the distance between the neutral and where the beam actually is 0. And similar story over here, the deflection at 0 is also equal to 0. Okay, is there anything we can do here? If there's no point load here, we can say that the shear at 0 is RA. That's something we could write. And here there's nothing of much of interest. Okay, now what is the slope? Now what the slope is basically, well, it is what it is, it's the slope. So take a point, say, a different point, say x1, and come down here and look which way the beam is. Is it falling down as it is here? Is it going up? Is it flat? And what you actually do is, now you don't draw a tangent to a beam, but if you were to describe the slope of the beam, you'd have to use the tangent, and that's exactly what the slope is. So at the slope of this line, y dashed of x1 is the slope. So the slope of the point is the slope of the beam. Is it going down? Is it flat? Is it going up? And the deflection is the vertical distance between the neutral and where the beam is under loads. Then, like, you're going to see stuff like this with a simply supported beam, you're going to see that the slope at 0 is negative, because you see it's going down. Whereas with fixed ends, we'll learn this later, the beam will come straight out of a wall, for example. So yeah, 6 variables. Distance along the beam, load per unit length, shear force, bending moment, slope, and deflection. And if you get confused between these, you're going to be in trouble. A lot of people think, for example, that the maximum deflection is where the bending moment is maximized. Not true. Things that are true are that the bending moment is maximized when the shear force is 0, but the deflection is maximized where the slope is 0, which is a different thing. So the other thing is we're going to get people confused between bending moment and deflection. They are not the same thing. Okay. So what have we seen? In this section, we learn how to formulate and solve beam equations so that we may calculate / estimate the deflection of the beam due to the loads on it. The estimation is about, we use a mathematical model that's not perfect, so it's really an estimate. This theory is known as Euler-Bernoulli beam theory. It's a simple model of the elasticity, and it was used in the design of the Eiffel Tower, and it's been successful ever since. Well, I say that, I'm sure it's failed. Because we're going to see the model, the theory makes some assumptions, but the assumptions mightn't actually always hold. Okay, so we're going to show a beam in a deformed state and an undeformed state. Well, we better do just the way, it doesn't matter. Let's do the undeformed state. So I need to get some straight lines going here. Now, of course, the beam is three-dimensional. Now, we'll never really draw it three-dimensional, but here we go. So it's in the undeformed state, and then if you put a load on it, you're going to get some deflection. Now, this is going to be hit or miss. That's not too bad. Oh, I have to draw this in. I'm not great at the drawing. Oh, that's pretty good for me now. Almighty. Yeah. Messed it up at the end. There we go. Okay, so undeformed and deformed. Now, even the way I've drawn this now is wrong, because you see the way that the beam is kind of squashed down here in the model. This won't happen. Okay, so let's see the assumptions, and there's a few of them. So the beams are assumed to be slender. Their length is much greater than their width. So they're really quite thin, because as they get larger in cross-sectional area, the mats behind, or basically the mats behind what we're doing, it doesn't actually work. So we'll often hear, what will the questions say? Well, they'll say different things. They'll say like a thin beam or something like that. Okay, the next thing, isotropic and homogeneous. So what this means is that the material is the same throughout the beam, and it's the same, so that's homogeneous, it's the same everywhere. It's not like it's stronger at the edges or anything like that. And isotropic means it's the same in different directions. So, for example, if you imagine a bit of timber, it's going to have different properties in, say, if the say the trunk is here, it's going to have different properties in the length in this way versus this way. And now I'm not talking about, what I'm kind of talking about is like if you made it, yeah, so like it's just that the direction doesn't matter basically. And then the other thing is constant cross section, and what that means is you don't have the beam squishing like this. Okay, so that's the assumptions on the beams, and the assumptions for writing down the maths is normals remain straight, they do not bend. Now what a normal is if I draw a vertical through the beam, say something like this. Now I think even I could make that into a kind of a yeah, I could even go further and kind of make that into a kind of a cross section. Well, if I could draw it, I'm not good at the drawing. So hopefully you see what I mean there is this is supposed to be, yeah, it's basically a cross section. And the line here is straight, and the line in the middle is the normal, and that even after bending it stays straight. Basically you're not getting twisting within the beam. Now in the real world of course it does, but then the maths is just too difficult to solve. So, and that's where you know, you'd have to be careful eventually that this model would break down for extreme situations. Normals remain unstretched, they do not change length. That's related to the constant cross section. So basically you don't get squashing of the beam, something like that. And normals remain normal, they stay perpendicular. So it kind of says that if you put some kind of a spike or a bar through the beam, like there'd be a 90-degree angle between the bar coming out of the beam, and even after deflecting, that you still have 90 degrees there. Okay, so using those assumptions, you can derive an equation that relates to deflection. And remember what the deflection is, it's this distance here, and the load per unit length at a point. Now, we won't derive this equation, but we'll just write down what this master equation is. It says that the Young's modulus of the material that comprises the beam times the second moment of area of the beam, so related to the cross section, the dimensions of the beam, times, and I don't think you've ever seen fourth derivatives before, but you know they work, just differentiate 4 times. The fourth derivative of the deflection with respect to the distance along the beam is equal to minus the load per unit length. Now where that actually comes from, we're not going to show you. If you really want to see where this formula comes from, I recommend Googling Spivak Physics PDF, and that will explain what's going on there. Right, so in all cases, the units knocking around are kilonewtons, and X is in meters, Y is in millimeters. So the units are all chosen in that way, and that means that the units of this and this must work in that way. Okay, now to solve this, you have to anti-differentiate 4 times, from the fourth derivative to the third derivative, from the third derivative to the second, from the second to the first, and the first to you find the deflection. So if you anti-differentiate this time 4 times, you'll find the deflection. Now every time you anti-differentiate, you'll pick up a constant. Now we're going to learn that the constants are, the first is the reaction at A, the second is the bending, no, at A is the left hand side of the beam, the second is the bending moment at A, the next one we call C1, and that is related to the slope at A, and the last one is C2, which is related to the deflection at A, which for us will always be 0. When I say us, in this module, because you could have something that is, say, fixed on the right and cantilevered on the left, and the deflection would not be 0 here. Now of course what you should just do is choose to look at it from the other angle, where the deflection of the cantilever is always 0 at 0. Right, so what have we got here? So the bending moment and the shearing force are related. So we've got a relationship here. It turns out that the derivative of the shear is minus the load per unit length. Now what that means is, and there's issues about the sign that we won't worry too much about, but it's saying how does the shear change? How does the sum of loads change? Well, the bigger the load per unit length, the bigger that changes. Okay. Okay, and then the rate of change of the bending moment is the shear. So what this tells me is Now there's a bit in it, you have to go into this into the Spivak to learn all of this, but it seems to me that you get, when you get loads, yeah, okay, I better not go into too much here. These are the differential equations. So it actually gives you a choice. You can do 4 anti-differentiations, or if you wanted, if you do 1, you find the shear. And then if you anti-differentiate the shear, you'll find the bending moment. Okay. So I've said you probably know more about shearing than me, either now or after doing your structural stuff next semester. So we'll just say that actually this is the definition of shearing. They can be combined, these two. This is what I said. If you anti-differentiate this twice, you get the bending moment. And then if you follow this through, if you anti-differentiate this twice more, you get the deflection. So it's saying rather than doing anti-differentiate this 4 times, you can do twice to find the bending moment and then twice more to find the deflection. And this is kind of typically what we'll do. Okay. Now there's a small issue with signs, which I won't worry too much about. So the plus minus is just really a choice. So you could get a bit confused, but it's just a convention. Just like we drive on the left-hand side of the road, it's not right or wrong. It's just so we all agree what we're doing. And this is saying that when you have a bending moment, we'll have positive bending moments, but you graph them underneath as if they were negative. Okay. So I'm just going to show you what I mean there. So say the bending moment went from 0 to a maximum and back to 0. You mathematically, and the maximum being positive, mathematically you'd graph it like that. But in this engineering, you graph it the other way around. So actually, rather than this being positive for the bending moment, the positive bending moment is down. Okay, so we're going to talk next about the different loads that we have.